Hi, I'm Wingyee Lau, postdoc at University of California, Riverside. I'm presenting to you a work to be submitted soon. This work is in collaboration with Jared Gillett at UC Riverside, Fred Hammond at UC Riverside, Serena Peralta at UC San Diego, and also Dave Rupke, Domenica Walezelek, and Nadia Zakamska. I'll begin with introducing why you should care about dusty quasars and the extremely red quasar population. Then I'll describe our KCWI observations of the Lyman alpha halo around the reddest ERQ of all. Then I'll talk about what we infer about the circumgalactic medium and the illumination geometry of this ERQ, and putting it in the context of quasar and galaxy evolution. The figure on the left is a part of that Hopkins figure showing the three intermediate stages in popular galaxy evolution models. Models predict that supermassive black holes initially grow in obscurity deep inside dusty galactic starbursts. At this stage, the hosts of supermassive black holes appear as ultraluminous infrared galaxies. The supermassive black holes grow until they are massive enough to power quasars. Outflows from the quasars then drive blowouts of gas and dust, which quench star formation. Then the blowouts reveal visibly luminous quasars in the galactic nuclei. Dust-obscured quasars are the middle stage here. They provide important tests of evolution models because they are expected to be young and powerful objects. They should appear during that brief blowout phase that is a transition between the initial dusty starbursts and later normal blue quasars. Many dusty quasar populations have been selected using different criteria. Many of these populations require more powerful physical properties than what could be attributed to orientation effects. Further, dusty quasars are the dominant population of the first quasars, so they're really unique laboratories. The Hammond et al. Team discovered a unique population of dusty quasars that they named the Extremely Red Quasars. ERQs are selected from the BOSS survey matched to WISE data. They are selected based on extremely red color from the rest UV to the mid-infrared. ERQs are at redshifts 2 to 4 and have high intrinsic bolometric luminosities greater than 10 to 47 ERQs per second. They have exotic spectral properties, most notably their O3 emission. The figure on the right shows the rest optical spectra of two typical ERQs. On each panel, I overplot a Sloan composite quasar spectrum for comparison. ERQs have the broadest and most blue-shifted O3 emission ever reported. The O3 outflows can carry speeds reaching 6,000 km per second. Because of the atomic physics, O3 lines trace outflows on KPC scales, which is galactic scale. The Vayner team and our team are studying adaptive optics observations on the O3. We both find that the ERQ-driven outflows happen on about 1 KPC scales, and the O3 emitting outflows carry enough energy to drive feedback in their host galaxies. To explore whether the ERQ-driven outflows have impact on the larger circumgalactic scales, which is tens of kpc, we need wide-field integral field spectroscopy, and we use the KCWI on KEC. Lyman alpha halos are ubiquitous around luminous blue quasars. For obscured quasars, there are not as many studies on their Lyman alpha halos. ERQs are ideal targets to advance Lyman alpha halo studies beyond random surveys or exotic single objects. ERQs can advance Lyman alpha halo studies to tests of galaxy evolution that are both statistical and specific. Our team is building a KCWI sample of ERQs. The pilot study is on the reddest ERQ. I chose J0006 plus 1215 for KCWI observations as it is the reddest ERQ. The on-source time was 70 minutes. Seeing was 1 arcsecond. Our instrument setting had a field of view of 16 arcseconds by 19 arcseconds and a spectral resolution of 150 km per second. The figure on the left shows a spectrum extracted from a 1 arcsecond aperture centered on a quasar. I call it the core spectrum. It has a narrow emission line at Lyman alpha, which was already noted in the Bose spectrum of this ERQ. The origin of this unusual spike has been speculated on. It's speculated to be gas on larger scales than the quasar broadline region. I used this Lyman alpha spike to define the systemic redshift, 2.3184, and on the figure I marked the wavelengths of nitrogen-5, silicon-4, carbon-4, and helium-2 in this systemic frame. I have a note about modeling the quasar point spread function. The broadline region is partially obscured, so the narrow lines can be identified as distinct components. To make a pure quasar template from this core spectrum, I clipped the Lyman alpha spike and the corresponding narrow emissions in carbon-4 and helium-2. I subtract the quasar point spread function, and then I optimally extract the extended nebula emissions in H1 Lyman alpha, carbon-4, and helium-2. The figure on the right shows the optimally extracted Lyman alpha image. The plus symbol marks the position of the quasar. The carbon-4 emission is also spatially extended. Detection of carbon-4 means the inner halo is enriched with past outflow events. The helium-2 emission is detected and is marginally spatially extended. I quantify the asymmetry of the Lyman alpha halo by calculating two asymmetry parameters. I define a flux-weighted asymmetry parameter which emphasizes the inner halo region, and I define a flux-unweighted asymmetry parameter which describes the overall halo morphology. I find that the inner halo on scales less than 30 kpc appears circularly symmetric, and the outer halo appears filamentary. I calculate the circularly averaged surface brightness radial profile of the Lyman alpha halo. I find that the profile is somewhat centrally concentrated. For the inner halo, I calculate the carbon-4 to Lyman alpha ratio and the helium-2 to Lyman alpha ratio. The helium-2 to Lyman alpha ratio is rather low. I create the Lyman alpha velocity centroid map as the first velocity moment of the flux distribution at each spatial position. Majority of the Lyman alpha emission have small velocity shifts relative to the systemic. The velocity field is quiet down to the innermost region. The velocity field is coherent in the inner halo and shows some shear from the northern edge to the southern edge. Together with the filamentary morphology, I think the northern and the southern edges trace inflowing streams. There is not enough signal to calculate a robust second velocity moment, so I do Voronoi binning of the Lyman alpha emission, and I fit a Gaussian to each spatial bin's Lyman alpha emission to get a velocity dispersion map. I'm not showing the velocity dispersion map here, but I can tell you the Lyman alpha velocity dispersions are comparable to the dark matter halo's dispersion. There is no evidence of gravitationally unbound outflows down to the innermost region. To further examine the kinematics, I define three apertures according to features on the velocity centroid map. I delineate an outer halo region and an inner halo region. I further divide the outer halo into a southern region and a northern region. The one-dimensional spectra extracted from these apertures are shown in a figure. I also overplot the 1 arcsecond core aperture spectrum on this figure. The Lyman alpha spike in the core spectrum has a line profile very similar to the Lyman alpha emission extracted from the inner halo aperture. This confirms that the spike in the quasar spectrum originates from the inner halo. Both the core spectrum and the inner halo spectrum have the same blue shifted absorption feature, which I mark with a vertical dashed line. This blue shifted absorption feature is absent in the two outer halo spectra. I think the blue shifted absorption traces a moderate speed outflow. I compared the J666 line-emitting halo with literature samples and single sources. These samples and single sources are Lyman alpha halos surrounding quasars selected by different criteria, and they are matched in bolometric luminosity and cosmic redshift to this ERQ. For type 1 quasars, I have the Kai et al. Sample, the Arigoni-Bataya sample, the Borisova sample, and the Mackenzie sample. For type 2 quasars, I have the Denbrock sample and the Sanderson single source. All measurements on the J666 Lyman alpha halo are within the wide and diverse ranges of measurements on other quasars. They have comparable nebular sizes, nebular luminosities, kinematics, with some marginal differences in the surface brightness radial profiles and asymmetry levels. I show a figure that compares the Lyman alpha nebular luminosities. The individual literature sources are plotted with small symbols, and the averages of the literature samples are plotted with large symbols. I find that the ERQ's Lyman alpha halo tends to be less luminous than type 2 powered halos. If I consider only the type 1 blue quasars in the figure, the nebular luminosity weakly increases with bolometric luminosity, with substantial scatter in a trend. Comparing J666 with this trend, the nebular luminosity of J666 would be 3 times lower. It implies that the suppression in the escape fraction of ionizing photons relative to blue quasars is about 3 times. But I also note that this factor of 3 deficit in nebular luminosity is well within the scatter around the trend. I show a figure that compares the flux-weighted and flux-unweighted asymmetry parameters. The flux-weighted asymmetry parameter alpha neb of J666 is higher than most literature sources, which means its inner halo morphology is less asymmetric than most. The flux-unweighted asymmetry parameter alpha QSO of J666 is similar to other type 1 sources and is higher than type 2 sources, which means that J666 overall halo is similarly asymmetric as other type 1 halos and is less asymmetric than type 2 halos. I also compared the inner halo helium-2 to Lyman alpha ratios. The J666 helium-2 to Lyman alpha ratio is similarly low as other type 1 sources and is lower than type 2 sources. Here are some implications from the analysis results on J666. The J666 Lyman alpha halo is not dissimilar to other quasar-powered halos. There is not much evolution in the halo emission across quasar colors. I think this is because the lifetimes of quasar episodes are short. The very fast outflows driven by the ERQ happen on galactic scales. Outflows on circumgalactic scales slow to moderate speeds and don't travel very far. The Lyman alpha halo of J666 is marginally more centrally concentrated, and the inner halo appears less asymmetric. These differences are consistent with the ERQ being young, and the outflow materials have not expanded to the outer regions. So the J666 halo is kinematically quiet despite very fast O3 outflows. At present, no selection criteria on quasar properties systematically find fast outflows on circumgalactic scales. The only selection criterion that systematically finds circumgalactic fast flows is radial brightness. The Lyman alpha spike in the 1 arcsecond core spectrum of J666 arises from the inner halo region. In general, narrow emission lines are good indicators of systemic redshifts. For other luminous quasars, their systemic redshifts are often estimated based on broad emission lines and are uncertain. Enabled by the extension in the ERQ, we're able to study the line emissions down to zero projected distance from the quasar position. We find that halo emission properties transition near a distance of 30 kbc from the center. The inner halo is dominated by moderate speed outflows and past outflows, and the outer halo is dominated by inflows. A fundamental question about the nature of ERQs is whether their obscuration is due to orientation effects or a global dust distribution. Orientation effects may be caused by a dusty torus and asymmetric ionization cones, as in the type 1 type 2 dichotomy. On the other hand, a more global dust distribution may relate to more dusty and younger host galaxies. I've estimated that the overall escape fraction of ionizing photons in J666 is suppressed by 3 times relative to blue quasars. With the shape of the J666 spectral energy distribution, the suppression in the line-of-sight ionizing flux is much larger than the suppression in the overall escape fraction. Obscuration is therefore anisotropic and is heavier along the line of sight than in the plane of sky. Although obscuration in J666 is anisotropic, I'll argue that it lacks the strong asymmetry as in type 2 sources. The dust distribution is instead relatively more global and patchy. An obvious clue is the type 1 emission line properties of J666 despite the extremely red color. Another clue is that the helium-2 to Lyman-alpha ratio of the J666 inner halo is as low as other type 1 sources, and is lower than type 2 sources. According to an argument in Cantalupo 2019, a low helium-2 to Lyman-alpha ratio implies that the observed Lyman-alpha fluorescent volume along the line of sight is larger than in the plane of sky. In turn, this implies the ionizing photons can escape along the line of sight dust distribution. So the line of sight obscuration is patchy. Yet another clue is that the overall morphology of the J666 Lyman-alpha halo is less asymmetric than type 2 Lyman-alpha halos. Due to different orientations of the ionization cones, type 2 Lyman-alpha halos should appear more asymmetric than type 1 halos. This is again consistent with J666 not having the type 2 kind of strong asymmetry. And I'll note that Hammond 2017 argues for a scenario where ERQs drive fast outflows that ablate and disperse dusty clumps in their host galaxies. This results in patchy obscuration on galactic scales. Here's a summary. The Lyman-alpha spike identified in the Bose spectrum of J666 is inner halo emission. In general, narrow emission lines are good indicators of systemic redshifts. I find no evidence of evolution in halo emission across quasar colors. Marginal differences between the J666 inner halo and literature sources are consistent with the ERQ being young. The overall J666 Lyman-alpha halo is kinematically quiet. No selection on quasar properties systematically finds circumgalactic fast outflows. The inner halo is dominated by moderate speed outflows and past outflows, and the outer halo is dominated by inflows. The transition is near 30 kbc from the center. Obscuration in J666 is anisotropic. However, the dust distribution is relatively more global and patchy than the type 2 asymmetry. All these conclusions about one ERQ need to be sustained by the full sample. The analysis is ongoing. Finally, I think ERQs are analogs of the first quasars. ERQs are younger and globally dusty, and they have a characteristic spectral energy distribution, which is flat in the rest UV despite extremely red color from rest UV to mid-infrared. I suggest two lines of future directions. First is to search for fainter redder quasars that are analogs of the first quasars and follow up on their extended emissions. Second is to search for signatures of quasar feedback other than fast outflows on circumgalactic scales, especially at later cosmic times. You may ask me for the literature data I compiled so that you don't have to repeat the effort. Thank you for your attention.